Welcome everybody. My name is Rasmus Bro from University of Copenhagen, and today we have Alberto Ferrer here, and he's from the Technical University in Valencia in Spain, where he has been working with process chemometrics for many years. And we're going to hear about something interesting, which is causality in the latent space. I guess it relates back to some of the work of McGregor and the German PhD student. Which was very interesting, I recall. So I'm looking very much forward to this. Now, Alberto, do you prefer if people ask questions in the chat, or do you prefer to have them afterwards, or do you have any preferences?
I think I would prefer after the talk. If they want to write in the chat, then we can after the talk, and we can recall them and address all of them.
Excellent. Okay, thank you. Well, please go ahead, Alberto.
Okay, so first of all, thank you very much, Rasmus, for your very kind invitation. Finally, we we got it, because I remember you invited me some time ago to do, I think, something similar like this. Yeah. Sorry for the delay. Too much. I mean, you know, the time is a resource and it's limited. Anyway, here I am. So it's a pleasure to share with all of you. I mean, trying to highlight one of the nice property of PLS. I don't know to what extent people is aware of this property, especially useful for process optimization in the context that nowadays we are involved in digitalized industry 4.0 or even 5.0, like some people start working in this digitalized environment. And the property is the causality in the latent space. This is, as Rasmus mentioned, an original idea from Professor John McGregor in one of working with one of his PhD student, Christian Jäckel, in the 90s. I had the opportunity to meet Christian Jäckel when I was visiting John at that time. And let's go. This is the outline of my presentation. We are going to, I'm going to address what some people call the data tsunami syndrome. Then to make a difference between if we are interested in explaining or predicting something, the consequences of both goals. The following bullet will be talking about useful models in digitalized industry. Then I will go deep into the causality in the latent space, the nice property of PLS, and I will show you an example, an industrial case study. Okay, so basically people nowadays working in digitalized environments are experiencing what some people call data tsunami. Okay, so people are, I mean, a lot of data can be recorded. There is clearly a change of paradigm and in different ways. I mean, there is a change in the number of variables and samples to manage from few to hundreds, thousands, or even millions. There is also a change in the nature of the registered data. So we're not only registering classical engineering variables like pressures, temperatures, flows, but images, spectra, sounds, text, and so on. Also, there is a change in the type of processes, not only parts or continuous or semi-continuous, but also batch or semi-batch process. Some people in the statistical area call this functional data. And also a change in the pace, flow of data coming in from days, weeks to milliseconds. Okay, so it's clearly the change of paradigm coming from the digital revolution. So probably all of you know about the big data context. So this is related to this change of paradigms in terms of volume, variety, velocity, and so on. So in this environment, I have read several what I consider worrying statements, especially from some people coming more from the data science or computer science area. For example, the first statement is that due to the quantity and speed of data production, new technologies could now solve major scientific and industrial problems solely through empirical data analysis. Okay, this is the main comment. Without the use of scientific models, theory, experience, or domain knowledge. In fact, the book I'm referring to is called The End of Theory, the data deluge that makes the scientific method obsolete. Second worrying statement is really regarding that we no longer have to be fixated on causality, just correlation matters. And the third one is that what some people call data fundamentalism, in the sense that with enough data, the numbers speak for themselves. So I browsing through internet, I found this nice picture regarding the, statistics is dead. Some people consider and deserves long live to data science. Okay, so it's kind of joke in my opinion. Efron in 2020 wrote a nice paper trying to justify why those pure prediction algorithms were, in a hype and was highly cited, highly successful. We refer to all these neural nets, deep learning, boosting, super vector machines, random forests that are able to operate at immense scales with millions of data points and millions of predictor variables. It's true that those machine learning predictive algorithms has their lights and their shadows, okay? In fact, as Efron already states in the same reference, they have become media darlings in their own right, but have sometimes produced embarrassing errors. And you have several examples of embarrassing errors produced by an inappropriate use of those machine learning predictive algorithms. Here is a very simple example of also extracted from the same reference. It's a study with almost 100 men, 50% of them suffering from cancer, and the other were normal people. And it's a genetic study, so the information coming from the gene expression of more than 6,000 genes, okay? Using a gradient boosting modeling and splitting the data set in training and test. Here there is a very nice model with a very low percentage of root mean square error. And here are the importance of the genes in terms of the gradient boosting model fitted. Okay, the most important is gene 1031 and so on. And Efron did a very nice play with this data set, because he was removing each time this is the original model, all the genes in the model, then the same model deleting the most important gene, then the second model deleting the 5 most important genes, 10 most important genes, and so on and so on and so on, even deleting more than 348 most important genes, okay? And in the last line you have, in the last row, you have the result, okay? The number of errors of all those models. You see that the last model deleting the most 348 most important genes have exactly the same performance as the model with all the genes. So the lessons is that myriad of weak learners can provide good performance. So the reason for this is that probably this gradient boosting model could be nice for the clinician trying to discriminate for new people, for a new person, measuring the gene expression of those genes, to what extent, what is the probability of having this cancer or not. But this model is not so good for discovering the disease's etiology, okay? To discover which are the vital few causal genes, okay? So this is a nice example that introduced my next point. So the reason is that the emperor machine learning predictive models has nice clothes, but they are not suitable for every occasion. Okay, so coming back to digitalized environments, is this true that in Industry 4.0 there is no need of scientific method, there is no need of causal models, there is only pure prediction and classification matters? I guess no. Okay, let's see. So let's move to the second bullet, to explain or to predict. Okay, if you go to ChatGPT and ask what's the difference between an explanatory model with respect to a predictive model, this is the answer I got. Explanatory models aims to understand and explain the underlying causal relationships between variables, while predictive modeling, the primary goal is to achieve high predictive accuracy on the observations, regardless of the interpretability of the relationships between variables. Okay, so here is a clear difference between an explanatory model and a predictive model. Let's look to these concepts using mathematical formula. Okay, here is the classical formula trying to connect the observation, the output, really measure the predicted output of our model, and this is the model. Okay, the function, the regressors, the explanatory variables, and the coefficients, the parameters to be estimated. Okay, so in a predictive model, this doesn't matter. Okay, what matters is the connection between what you measure and what you predict regarding your response. Okay, so how well your model is predicting your response. So you are just looking for accurate predictions. Okay, and for that you only need to get association between the regressors, explanatory variables, and the output. No more, no less. But if you are interested in building an explanatory model, then this can't be a black box. Okay, you need to go through this box and try to understand what is inside. Inside in what terms? Inside in the sense that you need to know which are the regressors involved in this connection and how do they affect the response. Okay, so which and how, because you are looking for interpretability, and when you are trying to do that interpretability, we have to be very careful on the way we interpret the parameters. Okay, so I will go back to this problem later on. In order to go for explanatory models and to go for interpretability, in the sense that what happens if I change one unit for a particular regressor, what is going to be the effect on the output. So this is in order to know exactly what is going to happen, you need causality in the relationships. Okay, so the difference is that in classical predictive model, we are just looking for algorithmic modeling. When you want to build an explanatory model, you are looking for a stochastic modeling. Okay, both type of modelings are are useful in practice. The problem is, as always, that you use a hammer for everything you need at home, for example. Okay, so now let's move through the next bullet regarding what are the useful models in digitalized environments. So I would like to bring here a George box, and here is a very nice book called An Accidental Statisticians. I do really recommend anyone to have a read of this very nice book on his memories. Okay, George Box used to say a very, very famous sentence that all models are wrong, but some are useful. Okay, so but are all empirical models equally useful in digitalized environments? And then I want to bring here also another big name. It's called John McGregor. John was is a very famous chemical engineering, and also he made his PhD in statistics under the supervision of Professor George Box. John is right now retired. Okay, so from John I got that This depends on several issues. The first one is the goal. The goal, John differentiate between passive versus active goal. The nature of the data, if you are using historical, he called happenstance data, so it means collinear, non-causal correlation, just association, or data from experimental designs. In this case, you are getting independent variation in the X because you are really producing causal correlation, okay? And also the type of empirical model used. So he differentiated the models built on the measured variables, as we usually do in linear regression, in random forest, in deep learning, support vector machines, that we are connecting directly the X with the Y, or if the model is based on the latent variables, as for example is the case of PLS, where the connection between the X space and the Y space is not done directly as it is done in the previous examples, but through the latent variables, and that makes a big difference. So, for example, passive goals. In passive goals, the model is used to passively observe the process. For example, this is the case for predictive modeling and maintenance, pattern recognition and classifications, or process monitoring, fault detection and diagnosis. On the other hand, active goals, the model is used to actively alter the process, okay? This is needed for process understanding, troubleshooting, optimization, improvement, innovation, and control. In the first example, passive goal, predictive, and pattern recognitions, only predictive models are really needed, and only association between X and Y is needed. No causal relationship is needed to build nicely and very useful predictive models. But in order to use your model for an active goal, for example, for optimization or for process understanding, we need to fit explanatory models. In this case, causality really matters, okay? So we really need to know if I change something in X, what is going to be the change in Y. For building this type of, for building the predictive models, just empirical historical data can be used, okay? But if you are interested in building explanatory models, you can go and do this based on first principle models or using empirical models, but from DOE data, okay? From experimental design data, not from historical data. Okay, so but what is the, if you go to a digitalized industry, you will discover that there are lots of historical data that are not coming from any experimental design. In fact, in my experience doing consultancy in industry, it is quite difficult that if you go to a process engineer responsible for a part of a process, they are very reluctant to run any experimental design. It could be the case that they are allowed to run some experimental designs in the lab, but it's very difficult that you convince them to run any experimental designs in the plant, okay, when they are producing the goods they are selling to the customers. But they have lots of historical data, okay, and those data are very, very useful for passive applications, okay, for building predictive models where just association is what is needed, okay? And here you can use all the machine learning models, whatever you want. I mean, some of them work nicely and perfectly. But on the other hand, if you want to build active, for active goals, I mean, for example, for process optimization, I mean, you need first principle, and it's very difficult to get a good bunch of first principle for fitting a model to predict the melt index in a full petrochemical company is not possible. I mean, so complex. I mean, there are no differential equations. I mean, it's completely impossible. Okay. Or DOE data, okay, is again the same problem. I mean, people are not, you are not being allowed to stop the production and to run any experimental design for some reason, because you have hundreds of potential factors. And another reason is that those regressors or those potential factors are correlated, are collinear, and you cannot move freely, independently, or orthogonal any of them. Okay, pressure and temperature are collinear in some way. So you cannot, if you increase pressure, probably you need to increase temperature. You cannot go and play with the plus minus plus and minus minus, as for example we would make for a 2 to the 2 factorial designs. Okay, so this is the main problem. And then there is a temptation. The temptation is, okay, why, if I use those lots of historical data for building, for building a causal model, okay? And then George Box say, okay, be careful not doing that, because you will crash. Okay, you cannot build any causal model using the classical models that connect the X space with the Y space using historical data, happenstance data. Okay, so right now, summarizing, if you want to build models directly from X to Y, no problem if you use linear regression machine learnings. Those models are useful for passive goals, especially machine learning are very nice for modeling nonlinearities, but be careful, they are black box. There is non-unique model. You can fit a lot, hundreds, thousands of similar models in terms of performance with completely different regressors, so they are not interpretable at all. Okay, but the idea that John and Christian Jäckel posed in the 90s is that if you not fit your model trying to connect directly X to Y, but you do this through the latent variables, then, like for example using PLS, these models are very useful for both goals, okay? For passive, the whats, and for active, the whys. Because those models have very nice property, uniqueness. You only fit one model, one PLS model, instead of hundreds of support vector machines or hundreds of linear regression models. You are able to discover causality in the latent space and interpretability in the latent space, okay? And the main reasons is because PLS not only model the connection between X and Y, but also models the X space, and this makes a difference. So the main idea of John McGregor and Christian Jäckel in 1998, in a paper published in IC Journal, was that, okay, it is possible under restricted conditions to use happenstance data for active goals. Okay, so summarizing, if you want to connect X to Y directly, you need first principles, you need experimental designs in order to build causal models. But you can do this using, or try to do this using historical data, if you connect both spaces through the latent space. Okay, next, move through the causality in the latent space. First, we need to explain what type of causality we are referring to, because causality can be defined in a very different, in different ways, okay? So we are going to be precise, and we are going to use McGregor's words, okay? Causality implies that for any active changes in the unstable variables in the process, the model will reliably predict the changes in the output of interest. This is exactly what we are referring to. So I was trying to, some time ago, I was trying to, find out some nice example to illustrate the difference between association and causality, okay? And my mom gave this puppet to me, and with the help of one of my kids, I recorded this video that I hope you enjoy. So in this video, you will see how this puppet is moving, okay? So you see that anytime someone pull down the cord, the limbs go up, and anytime the cord goes up, the limbs go down, okay? So you see that the limbs, okay, the arms and the legs are highly correlated, okay? But some people consider that correlation means causation, okay? So if this were true, whenever I move one of the limbs, the other would move, but this is not happening. Okay, maybe because the causality is not on the arm, but on the leg. But then if I move the leg, nothing happens, okay? So this is a very nice lesson, okay? Association doesn't mean causality, okay? Because moving a limb doesn't affect any other, okay? This is something that people need to know. Association does not necessarily mean causation. The only way to move the limbs is moving the cord, and the cord is the cause of this puppet, okay? So if you want to move your limbs, please move your cause, the cause of the movement of the puppet, okay? This is the main message of this puppet example. So trying to visualize, okay, is like these are the variables you measure, the movement of the arms and the movement of the legs, okay, left and right. But here is the cause of the movement, okay? So when you get the data, if you register the movements of your puppet, you are registering the data in the original space. And you see that all the limbs are highly correlated, but this correlation is just association between them, okay? The real causality comes from the latent space, which is really, in this case, the cord movement, okay? Whenever you move the cord, you are moving your puppet, okay? So this is a very nice, I hope, example of illustrating the difference between association and causality. So now let's see what is, let's try to explain or to transfer this idea into a process, okay? Imagine you have a process with several regressors, X process variables, and several responses, Y process variables, okay? Here, just a very simple example. Imagine that you only have 3 regressors, three inputs and 3 outputs, okay? And the idea is the difference between connecting something, connecting something directly or connecting through the latent space, okay? Let's see exactly what I want to say. Imagine that you want to change the Y, okay? And then for doing that, you move your X, okay? You move your X, okay? And you hope that if you move your X, your Y will be moving, okay? So if this were the case, it means that you have causality in the relationships, okay? And this is what you can get if you fit your model using first principle models or experimental design data. But if you are using just historical data, like in the previous puppet, okay, if you move a limb, you are not getting any movement in the rest of the limbs, okay? So the main message is that it is not possible using historical data, okay? If you move the X, your Y, you don't know what is going to happen, okay? The causality in the latent space means that when you move your process in the latent space, this is the core, okay, the core of the puppet, then it is going to create a change in the X space and in the Y space. This is the idea, okay? So only by moving the latent space, then you can create a movement in the X and in the Y. And the X and the Y are being moved respecting the correlation structure of your model. So here we illustrate the idea of causality in the latent space. Is the change in the latent space what creates a change in your X and in your Y? Okay, so this is the idea of causality. Okay, so we are going to take advantage of the causality in the latent space PLS property in Industry 4.0. Okay, we are going to see through an industrial case study. Imagine now that you have a more simple example, that you have, for example, 3 inputs and 1 output. Very simple, but it could be equally useful if you had 3,000 inputs and 1 or several outputs. Okay, just for illustrating, I'm choosing a simple example. And you feed the PLS. imagine you feed the PLS with two components, okay? First component, second component. Here you have the score plot, which is the projection of all the data you get into this latent space. And imagine you want to produce a particular response with a particular value, okay? This could be melt index, density, whatever you want, okay? And you want to build a product with a particular value for the response, okay? Then the idea is, okay, how to do that? Well, imagine that you fit a PLS model, okay? You connect the Y and the X through the latent space, okay? In this case, through the scores. And this is a matrix that allows you to predict, even a particular score, allows you to predict the response, okay? So in this case, you have one response, okay, Y this, and you have two scores, okay? And if you want to know exactly which are the scores that fulfill this Y desired, you need to solve for these equations, okay? Systems of equations. In this case, you have one equation, okay? One variable. You had two responses, you had two equations. And you have, in this case, two unknowns variables, who are the scores, okay? So because you have one less number of equations than unknowns, then in this case, you have a multiple solution, okay? So your system of equations has multiple solutions. This multiple solution is what we call the null space. And because PLS, in this case, fits linear relationships, in this case, the null space is in this case is a straight line, okay? But if you were using more complex, for example, nonlinear PLS or the PLS augmenting with squares or interaction or so on, so the null space would have other shapes, okay? But in this case, it's clearly a linear space, okay? Null space, I mean, what null space means, okay? Null space means that whenever you are moving your process through this space, then the X will change, okay? But this change in the X will not provoke any change in the Y, okay? Why? Because all these movements of X will be projected through the latent space, through the null space, but will not change the Y desired, okay? This is the idea of the null space. Then, from all possible solutions, which one is the best? Because it opens to the process engineer, for example, the possibility to operate your process in a different range of this space. It will not affect the response, but probably those different conditions, operating conditions, could have, for example, other nice properties, for example, lower cost, lower consumption of energy, lower contamination index, and so on, and so on, and so on. So in order to finally go through a simple example, I'm going to show you one of the examples come from one of our consultancy projects. In this case, the goal was to minimize the temperature gradient between light and dense phase beds of the catalyst regenerator in a petrochemical company. And available data we had, well, in this case, we are simplifying the original problem. So we are just showing you the 63 process measurements that finally we selected. In this case, we have two responses, highly correlated, and we were using more than 7,000 observations. In this case, are hourly data. So the idea of formulate the PLS optimization problems is now comes from the mathematical optimization area. You need to define the objective function. In this case, the objective function has several parts. The first part is exactly what you want to minimize. In this case, this is the Y desired, and this is the predicted from your model. And you want to minimize the difference between what you decide and what you get, okay? In this case, because we have two responses, this is a vector. This is a diagonal matrix, which in the diagonal, you can play, giving more or less weight to any of those particular responses. If you give the same weight, then it means that both responses are going to weight exactly the same in the objective function. The second term refers to the hot least square. the third term refers to the square prediction error, okay? Those both terms are called soft restrictions, because these restrictions, I will show you, forcing the solution to be as close as possible to the center of the historical data. And this one forces the solution to be as close as possible to your subspace. And the first one is trying to minimize the difference between the response predicted by the model and the desired one, okay? So you are minimizing in order to find the particular score configuration, score vector that fulfill the objective function. Then, as in any mathematical optimization problem, not only you can play with soft constraints, but you can also play with hard constraints, okay? Those constraints have to be fulfilled, okay? In this case, for example, you are forcing that based on the solution, when you get the scores and you get the new configuration of your process, the square prediction error will be below a particular limit, okay? This is hard constraints for the SP. Again, you are forcing that given the solution for the scores, the hot-length square for those scores in the projection in the subspace will be below the square limit, the control limit for the hot-length square, okay? An equality hard constraint for the hot-length. And also, this is something that process operators are very keen on. You are forcing that any solution will will respect the feasible or historical bounds on process variables, okay? So if a process operator is used to operate a temperature between 100 and 300, he or she doesn't want to get a solution outside this region, okay? Because if this is the case, he or she will not trust you. Okay, so let's see the application of this simple example to the idea of causality in the latent space to this problem. Okay, in this case, we fit a PLS model with 8 components, okay? These are the goodness of fit and the goodness of prediction. The goodness of prediction on the calibration, on the validation data set for the X and for the Y, okay? There is something very interesting in this application, is that usually people used to use PLS are only aware of the goodness of prediction on the Y space, okay? But mind that here we are going to invert our model, okay? So it means that we not only want to a PLS model who has a very nice performance or nice performance index for the goodness of prediction in the Y space, but also goodness of prediction in the X space, okay? So in this case, well, I'm not going into the details, but there are several process variables strongly related to the responses, but there are also some process variables with almost no relationships with the responses, okay? Mind that in this case, we are connecting 63 process inputs with 2 outputs, okay? Even though we have fitted and PLS with 8 components, here we are showing you the 2 most important, the 2 first components explaining most of the variability, okay? And here in color, I have plotted the score plot color by one of the responses, okay? Remember that we wanted to minimize the response, so the most blue, okay, the better, okay? So you clearly see that there is a clear gradient from high to low response, and because scores are orthogonal, then there is also an orthogonal direction. This is more or less the direction of the null space, where no matter if you are moving through this area, you are not changing the Y's, even though you are changing the X. Okay, so let's see the different examples after applying the mathematical optimization problems. And in order to illustrate the benefits of the soft and the hard constraints on this model, here I'm showing you the result, the outcome of the formulation, the mathematical formulation problems by using in the objective function, just the objective function that tries to minimize the response. There is no soft constraints, there is no hard constraints, okay? Here you have the two first latent variables, the third and the fourth latent variables out of the 8 PLS components, okay? Those fourth explain most of the variability of the PLS model. And here you have the original variables, Y1 and Y2, highly correlated, and this black circle means the historical minimum. The historical minimum is projected onto those spaces, and here is the black circle, okay? So let's see which are the solution if you try to minimize only one of the responses, okay? This is the null space for the first response in the scores 1 and 2, and this is the same null space in the scores 3 and 4, okay? Clearly you see, this is the same for the second, okay? And in this case you see that the intersection of both in this case is inside the score plot, but in this case is outside, far away to the total square control limit. So this is not a feasible solution because it's completely far away from your model. So I would never trust this solution, okay? The problem is that we have not used any of the constraints that I can use. So we are going to impose the hard constraints in order to force that all the solutions respect the historical restrictions for the process variables. Again, sorry, by the way, in the first case, this is the best solution, okay? It's 0 and 0 because you want to minimize, okay? Okay, this is the mathematical point of view is the best solution, but this solution is completely unfeasible, okay? Be careful because if you apply here any machine learning or linear regression, you will probably get this solution, okay? But this solution is not feasible. Okay, so if you impose the historical limits, then you see that the solution is slightly worse, but again, we have a problem because the solution is outside the model, okay? So again, it's an unfeasible solution. The only way to get a feasible solution is to use the soft, in this case, the soft constraints, okay? Or the hard constraints. In this case, we have used the soft constraints. And here you see you see that the solution finally is here, and in this case is here, and in the global Y1 and Y2 is here. So it's better than historical, is nice because it's lower and feasible, okay? And in this case, you see that you have been able, okay, to find out a solution that respects the historical benchmarks for the restrictions for your process variables. But it's very nice to see that in this case, it corresponds to an area that were not explored in the historical data, okay? So, I mean, in this particular case, we were discussing to the process engineers why, okay? They were in some way, they didn't expect this, okay? But based on that, they trust us, they apply this, and they got a better condition than historical. So in this case, we were successful because the optimized solutions were feasible. They tried this, and in fact, they obtained better, slightly better results than historical minimum. Mind that in a petrochemical company, a very small increment or improvement, okay, can give you a lot of money, okay, can save you a lot of money or can earn you much more money. Of course, this particular solution, if you project through the X space, implies that forces a particular combinations of the process settings, okay? Any of those process settings where have nice property in the sense that they respect the correlation structure and they were below or in between the historical limits, okay? So, but what could be a potential next step in this case? Imagine that your model, for example, is not good enough for building a reasonable PLS, because some people could consider which is the minimum goodness of performance for the, for example, goodness of prediction required for inverting your PLS model, okay? So this is a good question. I would say that I mean, in practice, in industry, you will never expect a very high Q-square goodness of prediction for I mean, a real PLS model fitted with historical data, because, you know, people in industry are not playing with their process, okay? They are not changing, they are not modifying in purpose a lot of things. In fact, the best process, real process, would be a process with a 0% of a goodness of prediction in PLS, okay? It would mean that the process engineers are doing a very nice job, because they are able to compensate for all the sources of disturbances, and they are able to produce the same product with the same quality. Of course, this is not possible, but, you know, you are not in a calibration scenario. You are not in a lab where you are modifying, you are changing in purpose the recipe. No. You are producing goods, and you want to sell those goods for fulfilling the customer requirements. Okay, so be careful. Okay, you don't expect to have a very high performance goodness in terms of, for example, goodness of prediction when you are fitting PLS with real process data. Sometimes 30%, sometimes 35%, 25%. Okay, but in this case, okay, try. In one of my colleagues, Joan Borràs, will show you in a next video, probably in 2 weeks, which are the consequences of this. Right now, I'm just going to tell you that what happens, for example, if you consider that your model is not well, I mean, is not, you have not enough excitation in your process to feed the PLS, okay? I mean, you can use this approach to find this optimized solution. You can let the operators to apply this solution, and I mean, let's see if your model has, if your process has improved, okay? But even imagine you want to go further, okay, farther away. Is this possible to run an experimental design in the latent space? For example, in this case, using only the 2 first component, or using the 3 first component, or the 4th or the 5th first component, using a full factorial or fractional factorial design. So you can apply all the potential of experimental designs methodology through the latent space, because in this case, you are no longer suffering from the same problems as I was telling you at the beginning of my talk, the problems of why people in practice don't want to run any experimental design in a real process, because they have so many different process variables potentially to be considered factors of that experiment that is almost impossible. And even though they select some of them, you can clearly see that some of them are correlated and you cannot modify independently any of them. But the latent variables do not suffer from that problems. They are very few, okay? And they are also, I mean, they are uncorrelated, okay? So you can clearly modify, no problem with going this way, this way, this way, this way, or in a 3 latent variables using a 2 to the 3, or in a 4 latent variable model go to the 2 to the 4, or in a 5 PLS latent variable go to the 2 to the 5 minus 1, which is usually the fractional factorial designs I usually recommend. And then operate your process for some time in this area, operate the process in this area for another time, operate your process in this area for another time, operate your process in this area for another time, collect all the data and refit again the PLS model, and do this, I mean, whatever you want, okay? So this is something that allows you to use all the power of experimental design, but in the latent space. Okay, so by concluding, I want to say that, rephrasing Professor George Box, remember that all models are wrong, some are useful. Second is try to find out the useful model in your context. Machine learning techniques are particularly useful for building predictive classification models, mainly when strong nonlinearities are expected. In this case, association correlation connecting X space through Y space is only needed, and for this, historical data are okay. But for process optimization, causal models are required. In this case, you can use FAIR principles or data from experimental designs connecting X through Y with original variables. You can use in this case, for example, machine learning, or you can use linear regression, or you can use latent variable based. So in this case, there is no problem. The problem is when you want to use historical data, because you have a lot of historical data in your plan. In this case, you could try to use PLS for restricted optimization. Mind that restricted is because it is not completely optimized, and you are not completely free of move all your process. You need to respect the correlation structure. You need to be inside the historical limits. That's why I call it this restricted optimization. It provides useful insight of the complex correlation structure between inputs and outputs. It gives you very nice insights on process understanding, and you can also use, if you want, subsequent DOE on the latent space to enrich the database and refit your model. Okay, so mind that statistical thinking is very nice, but the statistical thinking with the statistical methods are even better. And if you also incorporate to statistical thinking, statistical methods, machine learning, you will experience the power of what we call statistical machine learning. And remember, in digitalized environments, life is easier in the latent space. So I would like to thank some of my colleagues that have been involved in this research. My colleague Joan Borràs, Carl Duchens, Daniel Gonzalo Palafí, and also Professors Massimiliano Barolo and Pier Antonio Facco from Universitat di Padova, Carl Duchens from Université du Québec. And here you have a list of nice references for any of you who are interested in going deep into this exciting and nice property of PLS. And that's all. Thank you for your attention.
Thank you so very much, Alberto. And we already have some questions I can see in the chat. So one is from Tom saying, I think it's about when you would go in the other direction, looking at X, when would you score the model invertly, also looking on the X predictability?
Yeah. Tom, yes, exactly. This is a very nice question. This is referring exactly to what I was commenting on. When you feed a PLS, you usually consider the as performance index the goodness of prediction, okay, on the Y, okay. But when you want to go back and go from the, trying to connect both spaces, you are not only interested in predicting, because you know that once you get the scores, you have to predict the X, okay? So it's a prediction model to predict the X. In fact, we are using cross-validation also in the X space. So exactly, you are looking for a predictability on the X space. This is exactly one of the differences of when you are fitting a PLS model just for predicting the Ys, or when you want to use a PLS model not only for predicting the Y, but also to predict the X.
Excellent. We have another one. What are the advantages of PLS compared to the PCA LDA method?
You mean PCA for compressing and then using linear discriminant analysis on the scores as regressors?
I guess so, yes.
Okay. Of course, you could do this. You could fit a PCA and then use a linear discriminant analysis on the scores. And then, linear discriminant are assuming that you have something good, something bad, okay? So this is more related to what my colleague Joan, for example, will address, for example, when you want to discriminate between good quality or bad quality, or something that respects a particular boundary for your response quality property or not, okay? In theory, you could apply the same. You could feed a PCA, you could get the scores, you could feed a linear discriminant analysis, and then you could go back, okay? Then in this case, you need to go back twice, because first you need to go back to what are the scores, and then from the scores, you need to go back to what are the X by inverting the PCA. We have never tried it because basically, this is exactly the same as if you are not just, addressing the linear discriminant analysis, but for example, you could use, for example, a PCR, okay, which is PCA and linear regression, or you could, for example, feed your machine learning model, for example, your support vector machines, instead of using the original X, you could use the latent scores, or if you are interested in using, for example, a neural net, you could also avoid to use the original X and do first a PCA compression, feature extraction, and get the scores as an input for the neural net. So no matter, you could use plenty of methods, okay? I mean, my point is that, you know, PLS do this in one shot, okay? PCA linear discriminant, PCA neural nets, PCA linear regression, do this in 2 steps, okay? And you know, sometimes, I mean, probably if you are, for example, PCA, how many components are you going to feed in a PCA? If you follow some rule that, okay, extracting 85% of the percentage, it could be the case that in the 15 remain, in the very few are exactly the components that are really related to the Y. So I usually tell my students, if you want to use a PCR, no problem, do this, okay? But look carefully about what are the criteria to use the components on the PCA, okay? Because the number of components on the PCA depends on the goal of the PCA. So summarizing, you can do this. Yes.
Thanks. And we have a question from Jerome. I do not understand what makes this model causal if you can also swap X and Y, because you do not use information on the measurement errors here.
Okay. What makes this model causal is mine, Jerome, that, I mean, you know that causality could be I mean, defined in a very different ways, okay? I'm not telling you that based on my model, I am going to be able to discover exactly which are the pathway or the genetic expression.
Okay, yeah.
Okay?
That's what I had in mind, yeah.
No. I mean, that's why also I also say restricted. In fact, sometimes I say restricted causality, and that's why I decided to define exactly what I mean by causality. Causality means that if you change something in what you modify, then you will see a change in your response. This is our meaning of causality. Of course, for example, I have an example, example in another industrial study that out of the variables that were involved in these latent variables that were causing the movement of the model, only one of them was really the causality of the problem, okay? It could also be the case that none of the variables that you have measured are really the causal of your model. There is another something that you never measure, but are affecting, it could be the case. But our point is that by using this idea of the latent variables, you can go deep into your model and try to understand what is going on. Of course, probably, for example, once you discover which are the main variables associated to the main sources of variability in your latent space, you could try to run an experimental design in only that subset of process variables. So I guess that my point is that using this property of PLS could give you some nice insights on how to go deep onto your learning process. Okay, I'm not telling you that you are discovering the pathway or no. I'm trying to say, okay, if it's a way, right now, if you ask a statistician, may I use historical data for process optimization? You would get no. Now, the point is
very annoying.
That's our point. Okay, try. I think you have an opportunity. It's a window you can open. Sometimes you open the window and you don't find anything. Okay, but open the window. You could sometimes get nice information. This is our experience.
Can I ask something related to that? I like your little puppet and talking about causal, etc. But let's say that I put the movement of the arms in X and the movement of the legs in Y.
Yeah.
And we still have an unobserved cord moving everything. So I'm gonna claim that the legs are causing, or the whatever, you get what's your sort of
that's a good point. In fact, I usually consider, for example, that the X are the X are the arms, and the Y's are the legs, okay? X are not causing the movement of Y's, okay? X are not causing the movement of Y's. The only thing that causes the movement is the chord. Chord is creating a movement in X and in Y, okay? And then you are right. Several questions, okay? For example, what happened with the Y's? Can I have a puppet? Can you see my arms? Can I have a puppet this way? No. Because anytime I want to maximize this has to be maximized, okay? So there are several questions. In real practice, okay, are all X processes are manipulable variables? No, not all of them are manipulable variables. So there are several tricky points that you can incorporate in order to, to see how to put your puppet in a real process this way. Okay, so more things to discuss, but I want to stress that idea.
That makes sense.
Okay.
Can you comment on controlled versus passively monitored variables? That's kind of related to what you're just saying.
Yes. When you are interested in control, you need to model causality, okay? Because when you use control theory, control ideas, you want to counteract. For example, control could be feed forward. You see that you have some raw material properties that you know that are going to affect your quality properties. Okay, for example, the quality property is increasing 2 points above the target. Then you need to modify your process variables that you can manipulate in order to compensate for the change. This is feed forward. In feedback is the reverse. First, you see that your response is outside your target, and then you need to, for example, you need to go back to force your response to be exactly at target, and then you need to modify by using a transfer function model to change, to know exactly how much you should change your manipulator variable in order to compensate for that. For doing that, in fact, you need to fit a causal model. It's a linear regression. What people call transfer function model is a classical linear regression model fitted by experimental design, because process control engineers usually do some experimental changes by modifying the inputs and see which are the changes in the output. So control is exactly an active goal.
Right. Okay. You want to say something, Jeroen? I'll get to
Yeah, because I was actually thinking, so what you are, because you are calling a lot of things like causal, but in fact, what you said previously, that you actually need to have a 3-block model, where, well, doesn't matter what the letters are, but let's say X are your controllable variables, then Y are your observed X, your used observable X values, and then you have a sort set of outcomes which are Z. That would actually be, a more sensible model to method or algorithm to model what you were trying to do, right?
Yes.
Because
yes.
also, there will, in your controllable variables, there will not be, let's say, automatically a measurement error allowed.
Yeah,
because otherwise you have no control.
Yeah.
If you cannot set the point and then it's different than that.
Well,
in extreme,
everything
is possible, but in principle, yeah.
Very nice point. In fact, Joan, my colleague Joan Borràs will address this problem, for example, when you are dealing with raw material properties, process variables, manipulated process variables, and output. So a 3-block system. And in fact, we have exploited this idea by applying sequential multi-block PLS. Okay.
Yeah. This is what I was.
Okay,
and this PLS type things. Yeah.
This is very nice, because then you can orthogonalize and you can take out, based on the process variable that you have modified, you can extract what part of this modification comes in order to compensate for raw material properties and what part comes from other things. Okay. So, there are several.
This is personal, but this is what I remember from MBIS.
Yes.
Also?
Yes.
Yeah, you showed it there. Yeah. Okay. Yeah.
But Joan will also address this for defining what we call the raw material specific design space in the quality by design space, raw material multivariate specification limits. So it will the next talk will be we will address this topic. Yeah.
Okay, great. Thanks.
There was another question. Are you willing to share the slides?
Yes, no problem.
Okay, good. I will. If you send them to me, I'll put it as a PDF somewhere, and put a reference out on LinkedIn and on our webpage. And then there was another one. What program is used for the PLS optimization, and is that kind of stuff available in Python?
Well, in fact, we have coded this in Python. We have our own code. So there are some commercial software that also has implemented this optimization. This is our original software from John McGregor. Now it's sold to Aspen Pro MB. It's called Aspen Pro MB, in fact. But there are, basically, you can code by yourself if you are, familiar with mathematical optimization. In fact, we have already coded in Python.
Okay, nice. And the Aspen thing is commercial, right?
Yes.
Yeah.